if we look at something like this, right? Here's all of the visible relaxations that we see. And so when we look at the visible emission spectra for hydrogen, right, this is what we see, right? We see the purple, blue, green, and red. Um, and those are all associated with the electrons falling back down from different energy levels to n equals 2, right? So the red is from N3 to N2, the green is from N4 to N2, blue is N5 to N2, and the violet is N6 to N2. And the lines represent the gap between energy levels and not the energy levels themselves. So that's important. These lines are not the energy levels. It's the gap between them, the amount of energy that is needed to travel between them, right? So the lines of the spectrum converge at higher energies, right? You have smaller and smaller gaps, which is evidence, suggests that the gaps between energy levels must also converge as we go further and further away. And that is shown in the Bohr model, right? The Bohr model has these getting closer and closer together. This is not drawn to scale. This is just something to represent it and to be helpful. So here's a question now that we've talked about that. That was kind of a lot, and this is kind of a more abstract idea. So when I get there next week, we'll keep talking about this. I'm hopeful that I can find the right equipment and we can do some practical stuff in the lab. That would be fun to see this kind of stuff, but we'll see. So quick check. What do the lines on the hydrogen emission spectrum represent? So take a second. You have 4 options. What do they represent? What do you think? So the correct answer is they represent the energy gap between energy levels in a hydrogen atom, right? It is not the energy levels themselves. It is not the excited electrons or the relaxed electrons. It is the gap in energy, because that energy is what is released in what we see in the spectrum, right? All right, here's your next question. Why are drops to the N1 level not seen in the visible region of the electromagnetic spectrum? So take a second, read through those options, and see if you can figure it out. Correct answer is D. Emitted photons have higher frequencies than the visible region. They release more energy than is in that visible region, so our eyes can't see it. Our eyes can only see a very small portion of the electromagnetic spectrum. So they have a higher frequency and higher energy than our eyes are able to see, right? Okay, here's another one. Which electron transition would absorb the lowest energy photon in the hydrogen emission spectrum? Take a second and think about it. So the correct answer, this one was a little tricky, is A, right? That's because it is the smallest gap, right, between these. This would be more energy. And it said which electron transition would absorb lowest energy. Absorbing energy means that it's going from a lower level to a higher level. If it would have said release, right, then this would have been the correct answer, because that's going from higher to a lower. But when electrons are absorbing energy, they're taking it in and jumping up to a higher energy place, higher energy level, right? So here is one that's a little bit more confusing, right? We have the hydrogen emission spectrum, and we have what says up there, excitation to n equals infinity. So we've seen 1 through 6, but we know as we get higher and higher in energy, these levels get closer and closer together. And we represent the, actually, I want you to think about this. What does it mean to excite an electron to n equals infinity? So maybe write a sentence or two. What would it mean for the atom or the electron to give it enough energy to reach n equals infinity? Okay, so to answer the question, when you give an electron enough energy to reach n equals infinity, um, the electron escapes, right? Because n equals infinity is really what we call the edge of the electron, right? Or of the atom, sorry. So when you give it enough energy to reach the edge, it can escape from the pole of the positive protons here. It has enough energy to completely leave, right? Because these energy levels have converged to this point. So if it gets enough energy to reach there, it will just leave, right? And then you form a positive ion in that case, right? So n equals infinity is the edge of an atom. Get enough energy to get there, you can leave. Here's another interesting question. Why does the energy axis have negative values? Do your best to think through this and then answer it. Give me a second. So this is kind of an abstract thing about this, but it is essentially because the y-axis is the potential energy, right? And a short distance between oppositely charged particles results in low potential energy or a stable system, right? So that's basically like when you're close to the nucleus, the electron and proton interactions are more stable because they want to be next to each other, right? The further out you get, the less stable they get. So as the position of an electron becomes further from the nucleus in the higher energy levels, the potential energy increases, becoming less stable, right? And we can calculate the energy change in a transition using the difference between the final and initial potential energy values. So n equals 1 to n equals infinity, right? So your final value would be 0, right? N equals infinity is 0. And our initial value is negative 13.6 electron volts. So that results in a positive value of 13.6 electron volts. So that's basically saying this is the energy you need to reach infinity and escape, right? So that's why these are negative, because you need a positive amount of energy to escape from the nucleus, right? Or you can think of this as you need this much energy, a positive amount of energy, to jump from n1 to n2. So these are negative values relative to this infinity point. Okay, that was a lot. Emission spectra can be kind of tricky, but I want you to now look at these following questions and do them as homework. Some of them are a little difficult, so you can use the internet to help you figure out the answers to some of these. But I want you to try and think through them as best you can before you use another resource. I will post this part of the slideshow on to ManageBack so you can see it and you don't have to go back and watch through each of through this part, but I'm going to click through them as well and kind of read them out to you. So the first one is sketch an energy level diagram with 6 energy levels. Add and label arrows showing the following transitions, right? The absorption of a photon, a line in the hydrogen emission spectrum, and then the highest possible energy emission. Explain why we do not see lines on a hydrogen emission spectrum caused by drops to N1. So do this in your notebook, and I'll take a look at it when I get there next week. Okay. Second, your next questions are suggest why the energy level model may be less appropriate for predicting the emission spectra of a helium atom. So think about what's in a helium atom versus a hydrogen atom. And then suggest 2 reasons that atomic models have evolved over time. Your next set of questions is use examples from the subtopic to explain the relationship between evidence, models, and theories, right? So how does emission spectra and these transitions relate to evidence, models, and theories? And then can you do the same using examples from another IB subject? So pick some other subject and explain the relationship between these things. And then I believe this is the last one. Let me check real quick. Oh no, there's one more. What is the difference between an emission line spectrum and an absorption line spectrum? I did not necessarily talk about this. You might be able to kind of figure it out with this picture and thinking about what these words mean. But if you need to, definitely you can use the internet to help you figure that out. Then the last one is how can emission and absorption spectra tell us about movement? And I will post a link to a website that will actually talk about this. But you might know about this from physics or astronomy or something like that. But that is it. We will talk about these next week when I get there. Good luck and have a great day.